Have you ever been driving over one of those huge, massive bridges, and you get that little fleeting thought in the back of your head, how in the world is this thing not falling down? It's a totally fair question, right? When you think about the incredible forces at play. So let's dive into the amazing engineering that keeps our bridges standing strong.
But before we get into why bridges stay up, I think it's really interesting to look at why they sometimes, fail. And the number one reason is probably not what you're thinking. It's not usually some dramatic collision or a truck that's way too heavy. Nope. The biggest threat is often silent, totally invisible, and it works from below.
Get this, 60%. In the US, that's roughly the percentage of bridge failures caused by issues with water flow. I know, right? The biggest enemy of a bridge is often the very river it's trying to cross.
And this hidden enemy, it actually has a name, scour. And understanding it is absolutely the key to preventing a disaster.
So, bridge scour, what is it? Just think of it like a relentless, slow-motion sandblaster at the bottom of a river. As water rushes past the bridge's foundations, it literally picks up sand and gravel and carries it away, digging the ground right out from under the bridge.
And this image shows exactly how it works. You see, the water doesn't just flow past nice and smooth. It creates this powerful vortex, almost like a little whirlpool, right at the base of the pier. And that vortex acts like a drill, just churning up the riverbed and carrying it downstream, leaving the bridge's foundation totally exposed.
Okay, so how do we fight back against a force of nature like scour? Well, it all starts with the very skeleton of the bridge. Our first line of defense actually comes from a huge revolution in materials science.
For centuries, iron was the go-to. It was the best we had. But then, in the late 19th century, steel completely changed the game. It has a much higher strength-to-weight ratio, which means you can build longer, lighter, and way stronger spans. Plus, it's more ductile. It can actually bend a little under pressure instead of just snapping. That makes it far more resilient for the long haul.
And you can see this incredible story play out right here. We started with the groundbreaking iron bridge way back in 1779. About a century later, the Brooklyn Bridge comes along and really ushers in the age of steel. And by 1937, with the Golden Gate Bridge, well, that's a true masterpiece of steel engineering, designed to flex and survive in one of the toughest environments on Earth.
But here's the thing. Strong materials are just one piece of the puzzle. What happens if a single part does break? That brings us to this brilliant engineering philosophy, designing bridges to fail safely.
The principle is called redundancy, and really you can just think of it like a safety net. The entire goal is to design a bridge so that if one single part fails, the whole structure doesn't come crashing down. It's all about building in backup plans, alternate pathways for all that weight to travel.
A classic truss bridge is the perfect example. Just look at that incredible web of interconnected steel. If any single one of those beams were to somehow break, the forces it was carrying are instantly rerouted through all of its neighbors. The load finds a new path, and the bridge stays standing. That, right there, is redundancy in action.
The Steel Bridge Design Handbook puts it just about as perfectly as you can. The whole idea is to make sure that no single piece of the puzzle is so important that losing it causes a total catastrophe.
And engineers have three main ways of doing this. You've got load path redundancy, which is basically using more beams than you strictly need. Then there's structural redundancy, where different sections of the bridge actually help support each other. And finally, internal redundancy, where even a single component is designed to hold up even if part of it is damaged.
So we've got stronger materials and smarter, redundant designs. But what if we could give a bridge a nervous system? A way for it to tell us in real time, hey, I'm not feeling so great. Well, that's the next evolution in bridge safety.
It's called structural health monitoring, or SHM for short. And honestly, the best way to think about it is like a fitness tracker for a bridge. It uses a whole network of sensors to constantly measure the bridge's vital signs, things like strain, vibration, even tiny changes in temperature. And it's a whole system working together. You have sensors all over the bridge collecting data. That data gets sent to servers for storage and analysis. But the final, most crucial step is interpreting it all. This gives engineers a live, continuous health report on the bridge, letting them spot tiny, subtle changes that could hint at corrosion or fatigue long before it becomes a crisis you can see with your own eyes.
So, what's the next frontier? If structural health monitoring gives a bridge a pulse, the next logical step is to give it a brain. And that, of course, is where AI comes in.
Say hello to the digital twin. Now this is so much more than just a 3D model. It's a living, virtual replica of the physical bridge. It's being constantly fed real-time sensor data, so it mirrors the actual bridge's condition moment by moment.
I absolutely love this analogy from researchers. Think about JRVS from Iron Man. When Tony Stark's suit gets hit, JRVS is right there telling him he has 80% functionality left. That's pretty much what a digital twin is for a bridge. It's the AI constantly running diagnostics and reporting back on its health.
And this is where it gets really magical. A digital twin doesn't just show you what's happening now, it lets you predict the future. Engineers can run simulations on the virtual model. What happens if we have a major earthquake? What will 20 more years of heavy traffic do to this joint? It lets them find and fix problems that don't even exist yet in the real world.
So why don't modern bridges collapse? It's all about this incredible, multi-layered defense system. We use way stronger materials, like steel. We build in smart redundancies so they can survive damage. We watch them 24/7 with sensors. And now we're using AI to literally see into the future and stop problems before they can even start.
And all of this leads to a final, really exciting question. We are right on the verge of creating truly intelligent infrastructure. So if we can give a bridge a digital twin, what's next? Smart power grids? Self-monitoring water systems? I mean, entire digital cities? The possibilities are really just beginning to unfold.